The ergodic hypothesis is one of the most fundamental concepts in whole of statistical mechanics, and is of fundamental importance to relate the behavior of the single particles making up a system to the thermodynamic behavior of the system as a whole. The state of any system can be described by its dynamical variables. So, for example, the state of a single particle which can move only on a straight line can be described by two dynamical variables, which would be its position, q, and its momentum, p. Then we can imagine of drawing a graph, which we call the phase space, with the position and the momentum of the particle in our two axes. So given a starting position and a starting velocity or momentum to our particle will simply be that we put it in a given point of the phase space at the initial time. As time passes, then the particle will move across the phase space as it changes its position and its velocity. So, for example, it can be proven that if the particle is actually a harmonic oscillator, then it will describe ellipses in the phase space. If our system is not made by one single particle in one special dimension, but is made by many particles in 3 dimensions, like for example a gas, then we can no longer draw this graph on paper, but everything that I will say is still valid. Therefore, our system will still be evolving with a trajectory in the phase space, which will be described by its position, q, as a function of time, and its momentum, t, as a function of time. Or actually the collection of all the positions and all the momentums of the phase space. Therefore, any relevant quantity of our system, which we can write with the letter f and can represent the energy or the angular momentum or any other interesting variable of our system, will therefore be seen as a function of the position, q, and of the momentum, p, of our system, which will themselves, of course, be a function of time. Every time we perform a thermodynamical measurement, then we will not be measuring this function f itself, which changes a lot over time, but we will somehow measure a given time average of this quantity, which can be seen therefore as 1 over t, which is the observation time, times the integral from lowercase t to t plus uppercase t of f q of t, p of t in dt, where the curly brackets denote the fact that we might have way more than one single q and one single p. Then we can assume that every time that we perform this time average, we are doing so on a measuring time uppercase t, which is way bigger than the characteristic time scale which our system involves. Therefore, we can say that we are actually doing a limit of uppercase t which goes to infinity of this quantity. Now, we expect this to be independent of the measuring time t. However, computing this integral is very hard. First, because in order to do so, we would need to first know how the system actually behaves. We would need to know its starting position, and we would need to find a solution of the equation of motions, which describes the trajectory in the phase space. And this is impractical and impossible for most macroscopic systems. However, we notice that this integral doesn't really depend on the order in which our system goes from a state to the other, but only depends on the time that the system spends in every different state. Therefore, we can assume that we can rewrite this quantity as a different average, that is an average on the phase space dq dp under a given distribution, which we write as rho of q and p, which doesn't depend on time anymore. And of course here we need to multiply by our observable f. The assumption that we can write a time average as an average on the phase space is the ergodic hypothesis. And it turns out that it will make many systems tractable. And it is on this ergodic hypothesis that we will focus for most of our course. Turns out that this probability distribution rho can be determined by the ensemble of our system, as I will show you in the next few videos.